Welcome to EDU World Space.
For this problem, let's write down our given data. So we're given the mass of the base satellite to be 20 kgs, and we call that satellite A. The mass of the sub-satellite MB is given as 2 kgs. We also know that the initial velocity of the base satellite VA naught is 0, and the initial velocity of the sub-satellite VB naught is equal to 3j meters per second. So because the chord is inextensible, after it becomes taut, the component of VB along line AB must equal to VA. So let's draw an impulse momentum diagram. So initially we have our base satellite A, and we have our sub-satellite B. They are joined by the cable that isn't taut, and B moves in the vertical direction, in the y direction, with momentum mb, vb naught. The momentum of satellite A is 0 since it's not in motion. And the horizontal distance between satellite A and B is 300 meters. After the string becomes, or the cable becomes taut, again we have base satellite A, which now moves towards sub-satellite B with momentum ma, va. And this angle we'll call theta. The chord is now taut, and satellite B now moves with final velocity in the same direction and has momentum mb, vb, where vb is its final velocity. So again, this angle to the positive x-axis is theta. We also have another vector. So the momentum of this vector is mb v b slash a. So that's where v b slash a is the velocity of b relative to a. So now we have a taut string of 500 meters. And this distance between A and B is still 300 meters between the centers of A and B. So in this case, we'll draw it a bit better. The centers of A and B are separated by 300 meters. So that's our momentum of the system before the cable becomes taut and the momentum of the system after the cable becomes taut. And what we know is that linear momentum needs to be conserved. So from the conservation of momentum, we get the following. Let's conserve the x components and the y components. Let's resolve these two components separately. So the x components before is equal to 0. There are no x components initially, since b moves vertically and a is stationary. But the x components afterwards is ma va times the cosine of theta plus mb va again times the cosine of theta, and we have to remember that va and vb are the same. So the two satellites move off with the same velocity since the cable is now taut, plus mb vb relative to a times sine theta. So 0 is actually equal to, we substitute our values in here, 13.2 times VA plus 1.6 VBA. So we'll call this equation 1. We have one equation and two unknowns. If we do the same for the y components of the linear momentum, we get that 2 kgs into 3 meters per second, that's the initial momentum of satellite B, is equal to the final momenta ma va sine theta, final momenta in the y direction, plus mb va sine theta minus mb vba times the cosine of theta. And we get that 6 is equal to 17.6 times VA minus 1.2 VB relative to A. And we'll call this equation 2. So essentially we have two equations with two unknowns. We can solve for VA and for VB relative to A. And if we have VBA, we can then calculate VB. So if we solve 1 and 2 simultaneously, we get the following. We get VA to be equal to 0.218 meters per second, and the direction is at 53.1 degrees to the positive x-axis. And from the simultaneous equations, we get VB slash A to be minus 1.8, not 18, but 1.8 meters per second. And we know from here we can calculate VB. So VB is equal to VA, some vector mechanics, plus VBA. And this is equal to VA times the cos of theta plus VBA times the sine of theta in the I direction plus VA sine of theta minus VBA cosine of theta, and that's in the J direction. And hence, if we solve for VB in terms of the I and J components, we can then write the resultant VB is equal to 1.813 meters per second, and satellite B, the sub-satellite, moves off at an angle of 43.8 degrees to the negative x-axis.